In this module, we want to develop a way to describe the changes in entropy and internal energy of a system, describe those changes based on measurable properties like pressure, temperature, and volume. In order to develop a rigorous framework that relates entropy and internal energy to these state variables, we could define and derive what are known as the fundamental entropy and internal energy equations. And so to develop this framework, we'll start by just saying that our entropy is going to be a function of internal energy, volume, and number of molecules in the system. Right? If we're defining entropy to be a function of those canonical variables, we could then take the total derivative of the entropy, and the total derivative will look like this. Plus ds dv, constant u and n dv, plus ds dn, constant u v dn. Okay? Now, we have this total derivative, but we also know, based on the basic properties of entropy, that these partial derivatives correspond to 1 over temperature, pressure over temperature, and then the negative chemical potential divided by temperature. Right? And so we could rewrite our total derivative for entropy like this. dV minus dN. Okay? Now, this total derivative has a special name. This is known as the fundamental entropy equation. Okay? All right, so all the fundamental entropy equation is just the total derivative of entropy, and it relates the entropy to these parameters. Now, what we could also do, since we have the du in this equation, is we could rearrange the equation and solve it for du. So it can rearrange to solve for du. And in turn, we'll get the following relationship. This equation, which is just the total derivative of the internal energy, is known as the fundamental internal energy equation, or fundamental energy equation. So I'll write it as internal energy. And so this equation, since all we did was rearrange this one, it's equivalent to the fundamental entropy equation, but it's more commonly used, or it's a little bit easier to work with and think about, because there's a simpler connection to temperature, pressure, and the chemical potential, right? We find that du is just proportional to these things rather than proportional to the like the inverse of temperature. Okay? All right, so those are just the basic forms of the fundamental entropy and internal energy equation. But here we wrote them as the extensive version, right? Because the entropy and the internal energy here will depend on the change in the number of molecules in the system. We could also write intensive versions of these equations. Of fundamental equations. And what's nice about writing intensive versions of the equations is that they're going to be independent of the number of molecules in the system, or they're going to be independent of the system size. So that way, if we want to, do an analysis on a small system and then scale up our results to a larger system, if we use intensive equations, then the scale up won't affect the actual numbers that we get. And so in order to develop intensive versions of the equations, what we'll do is with the internal energy fundamental equation, we'll just take du and we'll divide it by n. And that will give us essentially the molar internal energy. Right? And so if we divide the left-hand side by n, we're going to divide the right-hand side by n as well. And what we're going to do is we're going to put the n in all of the derivative terms. Okay? So we have t ds over n there, p dv over n, and here we're going to have mu dn over n. Okay? All right? And so S over n, that's just going to give us the molar entropy. V over n, that's going to give us the molar volume. But when we have n over n, we're just going to get 1, right? The n's cancel. And here, if we're taking the derivative of 1, which is a constant, that's going to be 0. And so as a result, this entire third term is going to drop out. And so when we write the intensive version of the internal energy fundamental equation, we just get this. We don't need to worry about any sort of n dependence. We just have the entropy and the molar volume terms. So this is the intensive fundamental entropy equation. And you could also equivalently write the intensive fundamental entropy equation. So this is intensive fundamental, this is not, this one's internal energy, fundamental internal energy equation, and then this one is the entropy equation. Okay. Now, we have all these fundamental equations, and so just to kind of emphasize why these are useful is that these fundamental equations allow us to relate entropy and internal energy, that is, relate unmeasurable properties such as U, S, and also the chemical potential. We can relate those back to measurable properties. Such as pressure, volume, and temperature. And so if we do an experiment where we measure pressure, volume, and temperature, by starting with the fundamental equations, we could develop a thermodynamic model that relates these to these.